The next phase we're going to look at is the concentration of our chemical in the air in the subsurface. And honestly, in our risk assessments, it's quite often the vapor intrusion, the impact of the vapors of the chemical in the subsurface that make a difference. And we can also use the fact that some chemicals are volatile. They'll volatilize into the air to help the cleanup of it. So we're going to talk about volatilization. Volatilization, we're going to use Henry's law. So often the concentration of one phase, air, water, solid, can be related to the concentration in another phase. So we're going to use that for the air phase and for the solids, the next one. For air, it's Henry's law that governs the partitioning between the chemical dissolved in the water and the chemical in the air. There is also the partitioning of the chemical between the liquid chemical and air. Back to our setup here. So the chemical can come out of the gasoline itself into the air. That's the vapor pressure. We're going to concentrate on it coming out of the water. So it's dissolved down here in the water and it's coming out into the air. That we can calculate using Henry's law. The form of Henry's law that we'll use, we're going to use the dimensionless version of it. So the concentration of the chemical in the air, we're going to do benzene, is the Henry's constant, or Henry's law constant, times the concentration of our chemical in the water. So we have an exchange between concentration in the water and in the air. So we have a concentration in the water and a concentration in the air, and the Henry's constant governs the difference between those. So one version of it is dimensionless. You have milligrams per liter in the water, you'll have milligrams per liter in the air. There are other versions of it in other units. For example, if you just look up Henry's law constant for benzene, a number you might find is 0.055 atmosphere meters cubed per mole. So if you have a molar concentration of benzene, you can use that and you can get a partial pressure in atmospheres in the air. It's a function of temperature. And at equilibrium, again, we talked before about how it actually takes things time to get to equilibrium. We can convert between the units of air concentration, mass concentration. Concentrations in air are often quite low, so we use things like micrograms per cubic meter, or we might use moles per cubic meter. Partial pressure and parts per million volume are the three. And count this as one. Mass or molar concentration, partial pressure, and parts per million are the different ways to represent the units in air concentrations. And that's beyond the scope of this course. We can convert between those using good old PIV-NERT, the ideal gas law, PV equals nRT. So here's an example. For benzene, the Henry's constant is 0.22 at a room temperature. I think in the, whereas the benzene homework might be 0.20. In our exercise, we're going to use 0.20. So I have a 2,000 liter storage tank. It's half full of water. The rest is air, and it has dissolved benzene in the water. It doesn't have any gasoline in it. It just has dissolved benzene in it, 20 milligrams per liter. What is the air concentration of benzene in equilibrium with the water concentration? Well, from this equation here, concentration of air is the Henry's constant times the concentration of the water. 0.22 times 20 is 4.4 milligrams per liter in the air. What is the mass of benzene in the air and in the water? So the volume of air, so it's a 2,000 liter storage tank. So it's 1,000 liters of air times the concentration of benzene in the air, 4.4 milligrams per liter. So we have 4.4 times 10 to the third milligrams, or 4.4 grams. Or in the water, we also have 1,000 liters times the 20 milligrams per liter would be 20 grams. We can go the other way. We have 2,000 milligrams per cubic meter in the air was concentration in the water. So I just reversed that equation. So the concentration of benzene in the water would be 2,000 milligrams per cubic meter over 0.22 equals 9.091 milligrams per cubic meter, or convert units, that'd be 9.1 milligrams per liter. Now let's move on to our next step of our where is the benzene problem, where we're going to do the mass of benzene in the air in the subsurface. So again, we have this 10 by 10 by 10 meter contaminated zone. If we look with our microscope there, we see in the pore space, we have some NAPL, we have some water, and we have some air. So the air in this example is 0.15 of the total pore space. Could be a lot higher. So these numbers can be different. And we have the other properties there, and we're using Henry's constant here of 0.20. So this must be a little different temperature than the one I did before. So very simply here, concentration of benzene in the air is H times the benzene in the water. The benzene in the water is 12. So it's 0.20, that's H, times the concentration in the water, which is 12 milligrams per liter. That's going to be 2.4 milligrams per liter in the air. The volume of air is going to be, we just did this for water. Remember, we got 1,000 cubic meter box here. 350 cubic meters of that is pore space. 15% of that 350 is air. So it's the 1,000 cubic meters times the porosity of 0.35. That gives us our 350 cubic meter pore space times the saturation of water. Oops, I will correct this in your notes. Saturation of air, and that is 0.15. 350 cubic meter pore volume times 0.15 is 52.5 cubic meters of air. So I take that 52.5 cubic meters of air times the concentration of benzene in the air is 2.4 milligrams per liter. That comes out to 126 grams. I just wrote the unit conversion there. So it's 126 grams, or 0.126 kilograms. So far, the mass of benzene in the water, and I'll keep digits here, 3.486 kilograms, and in the air was only 0.126 kilograms. This could be different if we had unsaturated zone where it was mostly air. These could change quite a bit. So in summary, we get the air concentration from the water concentration using Henry's law. And once we have that air concentration, we just take that times the volume of air that we have, that section of the porosity, and then we have the mass of benzene in the air phase.